Welcome back. So we are ready to start again. So the last talk of this morning's session is by Weijun Xu from University of Oxford. Not Warwick has written on the program, and his talk is on defocusing mass-critical stochastic nonlinear Schrodinger equations.
Okay, so thanks for the introduction. And I would like to thank the organizers for inviting me here. So I'm going to talk about the joint work with Chenjie Fan on this mass-critical stochastic nonlinear Schrodinger equations. And we began doing this work 3 years ago. There is also a similar semester program at MSRI, and they brought two communities of people together. One is stochastic PDE, and the other is dispersive PDE, and we are from these two different communities. And so we met each other, and we were talking about whether there is something we can do together. So the most naive thing you can think of is just take one of his favorite Schrodinger equation and put a noise on it. So that's the equation we end up with. I dtu plus Laplacian u equals, let's say plus minus u to the 4 over d times u, and plus a noise, let's say u Stochanovich w dot, and with u0 in L2RD. So there are several things in this equation. So first of all, if we forget about the noise for a moment, this equation is called defocusing if the sign in front of this nonlinear term is plus, and it's called focusing if the sign is minus. And sometimes there is also a way of writing things for writing Laplacian put on the other side. Then this time, if you put Laplacian on the other side, then defocus and focusing, then you should swap the signs somehow. It's really important that the sign in front of nonlinearity is the same sign as this operator. Then that's called defocusing. Otherwise, it's focusing. And mass critical corresponds to that. The power of this guy is 4 over d. And you really start with u0 in L2, but not anything better than that. So that corresponds to mass critical equation. And we'll see later that, so when Hendrik gave this talk, there's a very, very singular noise here, and there is a parabolic term here, and the sign here sort of corresponding to the minus sign here when Hendrik gave his, doesn't matter. So when Hendrik gives his talk, the sign in front of Laplacian is minus, and the sign in front of this guy is also minus. So that corresponds to a very, very strong damping term. And we will see later that, while of course in that equation plus and minus, it plays a huge difference. But we'll see later that in this type of equation, the sign of plus minus plays a difference if the power is 4 over d. But if the power is less than that, there is a difference, but the difference is not so big somehow. And because we are starting with L2 initial data corresponds to the critical problem, so the reasonable thing to start with is some sort of very reasonably nice noise. There are works on singular Schrodinger equations with quite singular noise, which means space, the white noise in space. There are papers by Hendrik and Arnaud Dabuche and also Massimiliano with his collaborators. But here, sort of, in order to consider mass critical problem and to look at the long-term behavior, we are looking at the evolution in a low regularity space. So it's sort of, we don't know how to do singular noise at this moment. So basically, we assume W to be very nice. So WTX is we look at the noise which is white in time and colored in space. So for simplicity, we just assume this W is Brownian motion times a very nice function in space. You can think of Schwartz function or CC infinity or whatever, but as long as it's white in time and very nice in space, so things should be fine. And the main result, so the main motivation we want to do is that we want to understand the long-term behavior of the solution U as t goes to infinity. So what does this solution look like, whether it's different or similar as in the deterministic case. So as a first step in understanding the long-term behavior, the first thing you want to know is that to ensure that the solution does exist globally. So So with Chenjie Fan, we get that in the defocusing case, which corresponds to a plus sign in front of nonlinearity, for every U0 in L2R, there is a unique solution. There is a unique global solution in certain sense, and I'll mention in what sense it is. So basically, it satisfies the Duhamel formula in certain space. And so before we go into the stochastic problem, let's first look at the deterministic problem to see what are the subtleties and what is known in the deterministic setting. So to distinguish, I wrote V for the solution to the deterministic equation. Let's say I dtV plus Laplacian V equal to plus minus V. Let's put the nonlinearity like 4 over d minus epsilon, because there is a big difference when epsilon is positive or when epsilon is 0 times V. And V0 is belong to L2. So basically, when epsilon is positive, this thing corresponds to mass subcritical. When epsilon equals 0, this guy corresponds to mass critical. So when it's subcritical, the plus minus sign here is not hugely important, but when it's critical, it does make a big difference. And we'll see, so these are type of evolution equations. We want to get a solution which is an evolution in sort of a certain function space, for example, L2RD. And in order to get this type of evolution, we first need to get this evolution local in time somehow. And the standard way to get something local in time for this evolution equation is to set up fixed point map. One fixed point. So in order to do local theory, let me call this nonlinearity, let's call it f of v. For local theory, is that we want a fixed point map, want a fixed point for the map gamma v of t equals e to the it Laplacian acting on the initial condition minus 0t, and this operator acting on the nonlinearity. That's the Duhamel formula, f of vs ds. So that's the standard setup for local theory. But in order to get a fixed point for this map, you basically need two ingredients. First of all, you need a space, which this map sort of takes an element in this space into itself. And second, so you actually need two ingredients. The first, that you need a space, let's say x, such that gamma maps x into itself. And second ingredient is that you need something small. That makes gamma a contraction. So there are two ingredients you need for local solution theory. And if we look at the space, so if we start with initial data, which is nice enough, say HS, if the initial data is nice enough, say HS in RD for s bigger than half the dimension, and because this space is an algebra, if s is bigger than half of the dimension, so basically there is no problem in controlling the nonlinearity, so you just end up with the same space. So basically we said that if your initial data is nice enough, you can just keep evoluting in the same space and there is no problem at all. But what if the initial data is below that threshold? You basically can't get evolution without in the same space without using something else. So when the initial data is below that threshold, the space is provided by something called Streethouse estimates. So basically, it tells you that you can look for evolution in Lebesgue space, which is LQ in time and LR in space, with Q and R satisfy certain relation. So the reason you choose this space is because of Streetchart estimates, which tells you that this evolution operator, so the Schrodinger operator, when it acts on some function, let's say f of Vs ds, and you look at this LTQ and LXR norm, I use it as shorthand for its LQ in time with evolution in the space of LR. It's actually bounded by, well, let me say, for any pair Q and R satisfying this relation, we call QR, which is admissible. So if you take any two admissible pairs QR and Q tilde, R tilde, the Streetchart estimates tells you that if you look at it, this quantity in terms of QR norm, and it's actually bounded by f of V in terms of its LT Q tilde prime, LX R tilde prime norm, where this prime means that they are conjugates of Q and R. So basically that's true for any two arbitrary pairs, QR and the Q tilde and R tilde, satisfying this relation. So that actually gives you a lot of flexibility in dealing with these things, because sort of at least when f is some polynomial or some power of V, there is a flexibility in choosing this Q tilde and R tilde here, and then you play with holder to get back to the same space, Q and R on V. So somehow that gives the space thing. So that's why, so this Streetchart estimate gives you a space in the local theory. And now we have a space, we also need something small in order to make it a contraction. If we just look at the initial data to be in L2, the deterministic problem with L2 initial data, and the nonlinearity, if you just control it, say f of Vs equals Vs to the 4 over d minus epsilon times of Vs, and the nonlinearity controlled, you would get with a certain thing, let's say LTQ and LXR, if we only look at time to be 0t up to some capital time t. And this is actually going to bound it if you play with the other pair Q prime, R prime, and play with holder a little bit. And actually what you will find is that you have a power of t, which depends on epsilon, and times V of the L2 norm, LT infinity L2 norm, to some power alpha, and times the other V of the same LTQ LXR norm to some power beta. And the point here is that gamma epsilon is positive if and only if epsilon is positive. So that's where we see the notion of criticality or subcriticality comes into play. So in other words, when when epsilon is positive, you get a positive power in front of this time. So basically, the local existing time, you can choose it depending on the L2 norm of the initial data only. Then that gives you a contraction. But when epsilon equals 0, you don't have this term anymore. So in order to get a small quantity for contraction, the existing time actually needs to depend on the initial data for its own profile, not its L2 norm only, but it has to depend on the whole profile of the initial data. So a consequence of this thing is that in subcritical cases, in subcriticality, in subcritical situations, if you have local existence, and you have a priori control on the L2 norm of the solution, a priori bound, it just automatically gives you global existence. And we see in this deterministic case, whether no matter the sign is plus or minus, there is the L2 norm is always conserved in time. So the L2 norm doesn't change in time at all. So you get a priori bound for free in terms of the evolution in L2. And then if epsilon is positive, the local existence time doesn't depend on the initial data. It depends on the initial data through its L2 norm only. So as a consequence, if you have conservation in L2, then every time you can just extend by the same amount of time, which automatically gives you a global existence. But in critical situations, when epsilon is 0, then things are different. In this case, even if we have a priori bound, in the sense that even if epsilon equals 0, we still have conservation in mass, so the L2 norm of the solution doesn't change at all. But the difference is that the existence time depends on the initial data, the whole concrete function, but not only its L2 norm only. So even if you have an existence time at the beginning, you run a little bit, then you get to some time t. And now even though at time t, the function has the same L2 norm, but it's a different function, and there is actually no guarantee that you can extend for the same amount of time later, and so on. And actually, so you see, in the epsilon positive case, that is subcritical, no matter the sign is plus or minus, you actually get global solution. It's just because of that. But when epsilon is 0, global solution, well, first of all, counterexamples are constructed for the minus sign, in the sense that for pretty much arbitrary initial data, which are not too small, you can construct, so your solution is just going to explode in finite time. So, let's say for epsilon equals 0 and focusing, there are blow-up solutions. And one can even construct this solution, this blow-up solution, very explicit. You can just write down what the solution is somehow. And then it also turns out that as long as you start with negative initial energy, your solution has to blow up in finite amount of time. So that is, so the blow up mechanism is quite sort of, yes, so there's sort of no chance to do long-term behavior for the focusing mass critical case, because it just says that as long as you start with negative initial energy, then you will blow up. And also, but for epsilon equals 0 and defocusing case, that has been an open problem for quite a while. So there has been papers by Kilip, Tao, Weijun, and Zhang. There are actually 2 to 3 papers by different subsets of these people. So basically what they say is that in the defocusing mass critical case, epsilon equals 0, say V is global, if V0 is radial. Somehow. There are 2 to 3 papers by different subsets just discussing in different dimensions. They first do dimension 4 and higher, and then later dimension 3, and then later dimension 2, something like that.
That's because subleft embeddings are stronger in the radial case?
I actually don't know why radial may be, but in the other way, so the dimension also plays a role, because when in dispersive problems, so higher dimensions are sort of easier than lower dimensions because you have better decay of the solution. And then later, there are very recently, so there are 3 papers by Dodson, which essentially remove the assumption that V0 has to be radial. So Dodson says V is global and actually scatters if V0 is in L2. So the first d bigger than equal to 3 case was in 2013, I think, and d equals 2 case is in 2016, and d equals 1 case also published in the same year. Somehow he essentially removed the assumptions and establishing a global behavior, the global solution, and actually it scatters. So scatters just means that in long time the solution behaves like a solution to a linear equation, but with a different initial data, somehow to that guy. And the bound we are going to use in our stochastic case is essentially that. So Dodson theorem, we are going to use this bound in the sense that, so for every V0, say there exists C, which depends on the L2 norm of the V0 only, such that the street chart norm, say LTQ, LXR, on the whole real line is bounded by this constant. And the essential thing is that this constant depends on the initial data through its L2 norm only, somehow, which is something you don't really see in the critical situation. I'm going quite a bit faster than I expected, but never mind. Okay. And a proof of Dodson, and in Dodson's proof of his theorem, he employs something called concentration compactness. So basically, it's a contradiction argument saying that if things blow up, then it tells you that, then the structure of this equation tells you that it can only blow up in a certain number of ways, which you can explicitly write down. I mean, typically, depending on how complicated the situation is, the number of ways can be anything between 3 to 10. And then you check them case by case and see that they are not counterexamples. So, and then you conclude that things don't blow up somehow.
I have a question.
Yeah.
So in the first papers, Tao, Bisan, and Zhang need a radiality assumption. Is it because you want your decay to be the same in all directions? Because if you are not radial, then it might be possible that you are decaying very fast in some directions, but you might have one direction where it's not decaying that fast, and then concentration compactness basically takes care of that. I think that even if you have a direction which you are not decaying too fast, almost like a traveling wave, the concentration compactness is saying that it still cannot decay too worse.
Oh, maybe it's that. I'm not. Yeah, to be honest, I'm not too familiar with the techniques in the above papers, but we can talk more. So I'll be interested in know more of that. But sort of, yeah. Thanks. And where were we now? Oh yeah. So Yeah, so these things are established by concentration compactness argument. And the reason they did 3 and then 2 and 1 is that sort of the decay in long term is best in 3 or higher dimensions. Somehow, essentially, it's because if you have the free Schrodinger operator, and this guy has smoothing in the sense that it maps L1 to L infinity. If you start with the solution with initial data in L1, you look at a free equation only, then the solution will be in L infinity. And it actually decays like t to the minus d over 2 somehow. And the reason bigger than equal to 3 is okay because that's going to be integrable for large t. And dimension 2 is at a borderline case. It just fails to be integrable, and dimension 1 is the worst somehow. It's not going to be integrable. Yeah, so back to the stochastic case. So what we consider is d equals 1, but actually we don't really see the difficulty between different dimensions because we just heavily rely on Dodgson's bound. So as soon as you assume this bound is true, you don't really see the difficulty between different dimensions in the stochastic case. And actually we wrote in the case d equals 1 because it's sort of the pairs coming as integers. But it's just going to be true in all other dimensions. So if we look at this equation, I dtu plus Laplacian u equals, we do the focusing case 4 over, d equals 1, that's power 4, plus u, Schrodinger, which is a very nice noise w. And so if we look at a stochastic problem, I mean, in dimension 1, this 4 corresponds to critical. But even for the subcritical problem, as we talked about earlier, so the first thing in setting up a local theory is to find a space. But even in the subcritical problem, say subcritical, I say I dtu epsilon, Laplacian u epsilon equals u epsilon, let's say 4 minus epsilon times u epsilon plus u epsilon. Let's say u0 is in L2. Even in the subcritical problem, so the setup of the space is not that immediate in the sense that because somehow you have a stochastic term here, so sort of the natural space you want to look at is sort of some integral, some L root space in omega, which maps every random input into something like LT infinity, LX2, intersects LTQ, LXR. That's how some sort of the most natural space to look at if you want to set up a problem. And then, but the issue is that because we have a nonlinearity here, so the integrability in omega just doesn't add up well in the nonlinearity. So you sort of can't close up as a map which takes something into itself. And the normal thing to do, it's actually done 20 years ago for positive epsilon by de Boer and de Bush. And where's the paper? I sort of, the Bush, almost 20 years ago. And also later there are various refinements by Michael Rockner and his collaborators, Babu Rockner and Zhang. Well, they do it in different ways, 2014. But what de Boer and de Bush did is that since you can't really set up a space for the fixed point problem right away, so what you do, and the problem is caused by the fact that the integrability in omega doesn't add up well under nonlinearity. So it's natural to introduce a truncation in front of nonlinearity. So you just kill the nonlinear term if the norm of the solution reaches some point. So basically you define um epsilon plus Laplacian um epsilon, sufficient time, equals, let's say, you introduce a truncation function phi, which which becomes 0 if that norm reaches a very large number m. Let's say nonlinearity and plus the noise term. And phi m basically look like that. So it's 0 here. At 0, it's 1 until a very large value m. Then it starts to decrease, let's say. It becomes 0 and just vanishes after 2m. So basically, this nonlinearity, you didn't do anything until the solution, this norm of the solution reached m, and when it reached 2m, the whole thing just disappears. So with this truncation, you can actually set up a fixed point problem for every m and every epsilon. And what the Bood and the Bush proved is that for every positive epsilon, um epsilon is Cauchy in a certain space L omega rho something in M. Then you can just send M to infinity to remove the truncation and get a limit, and the limit actually satisfies the equation or the Duhamel formula of the equation without the truncation. It's just up there. But they essentially rely, in order to show this uniformity and in order to set up a fixed point problem, they essentially rely on the fact that this epsilon is positive, and partly because the Dalton theorem were not available during that time. So we were thinking that since the deterministic thing is true, it's probably quite likely that you can have a similar statement, or you can have the same global statement in the stochastic case. And the thing we start with is the Bush solution um epsilon. Say there is such an um epsilon for every positive m and every positive epsilon. But then in order to get a solution to the critical case, you actually need to send m to infinity and epsilon go to 0 simultaneously or in certain order. And so with Chenjie, what we did is that we basically essentially proved m epsilon is uniformly bounded in both m and epsilon in a certain space, let's say L rho of omega, which is LT infinity Lx2 intersects of LTQ Lxr. So the certain norm of um epsilon is uniformly bounded in both m and in epsilon. So the two main ingredients is the Dalton theorem, Dalton's bound, and the other ingredient we use is also a version of concentration compactness. A version of concentration compactness, but it's sort of, if we assume Dalton's theorem is true, then we can actually employ a much simpler version of concentration compactness than Dalton's original paper, which basically let us check 5 or 6 different cases. Somehow, basically, you say if these things are not bounded, then they blow up, and if they blow up in a certain number of ways. Certain number of ways means 5 or 6 ways you can explicitly write down, and then you check one by one and see they are not counterexamples. So we basically conclude that things are uniformly bounded. And once we are assured that these things are uniformly bounded, you can just use this uniform boundedness, say, and the second step is that um epsilon is Cauchy as m goes to infinity and as epsilon goes to 0. Somehow, that's once you have a uniform bound. It's not straightforward, but it's sort of that we are quite assured that we can conclude the convergence with the help of this uniform bound. And one other way to mention is that whenever you try to employ concentration compactness thing, then things are going to be a mess. And then later we figure out there is one way to get around of that, being that we are requiring this uniform bound in both m and epsilon. It's mainly because the uniformity in epsilon that requires us to use the concentration of compactness. But if we only require uniformity in m without epsilon, then we actually don't need that messy sort of things. So actually, later what we realized is that, so in the Debord and the Bush paper, they start with um epsilon, and for fixed epsilon, they send m to infinity. And now, we realize what we can do is that we fix m, we keep the truncation there, and send epsilon to infinity first. Then what you get is the solution to the critical equation with the truncation. So um epsilon can converge to something called um as epsilon goes to 0. And it's because of the existence of the truncation, so all the bounds are there already in terms of this m. So with this m, you can easily send epsilon going to 0. And then in order to prove uniform boundedness in m, for m only, you actually don't really need this concentration compactness. Well, it's because you already get rid of epsilon in this way. So then you sort of send m going to infinity, and you get sort of u. Here, that's a particular way of taking limits that get rid of use of these messy things. But on the other hand, if you employ this type of things, then you can say that you can take limit in whatever order you want somehow. They do exist a limit, and this limit does satisfy. So what we did with that, so we construct u. So for every u0 starting from L2, we constructed a global flow u in L rho of omega some strata space that satisfies the corresponding Duhamel formula. And later, Deng Zhang, he's a student of Michael Rockner, 2018. He also came up a construction of the global solution U, but in any dimension D, construction of U in any dimension D, but sort of under a slightly weaker space in sort of H minus 2 something, under a slightly weaker space. So it's not satisfying the Duhamel formula, but satisfying the corresponding thing for the weak solution that in H minus 2. But it's pretty clear that these two things, you can relate these two things equivalently somehow. And and that's the statement saying that in the math critical case with a reasonable noise, you still have global solution. And also we did it in the defocusing case, actually with a plus sign. But even if you have a minus sign in front of the nonlinearity, the construction is the same if the initial data is small. The reason is that in the deterministic case, even in the focusing case, if the L2 norm of initial data is smaller than the ground state, then you still have a global solution. It's just that if your L2 norm is not too small, then you can construct counterexamples. And since that thing is true in the deterministic case, it's going to be true in the stochastic case as well. So if you start with the initial data which is below the ground state, then you automatically also get a global flow for that. So in the focusing case, it's a global solution if your initial data is small. And also, so the original motivation we want to do this type of thing is that we want to understand the long-term behavior. But so far, so the existence of a global solution actually doesn't immediately tell you what the solution behaves in long term. So that's what we want to investigate in the future direction. The first of all is the long-term behavior. And in the defocusing case, we are hoping to prove some type of scattering statements, may or may not be true. And in the focusing case, and of course for initial data large enough, you won't be able to get global solutions, but it will be nice to understand the blow-up mechanism. I think in the deterministic case, these things are pretty nicely studied in the sense that you can actually construct blow-up solutions which blows up precisely at whatever points you prescribe somehow. In the deterministic case, you are given arbitrary endpoints, you can actually construct blow-up solutions which blows up at these endpoints simultaneously. That's in the deterministic case. In the focusing situation, there are results like that. But in the stochastic case, even if there is blow up, it would be very nice to understand how things could blow up. And and the second is that, so the statement here is pretty stochastic analytic because it's sort of not in any sense pathwise. It's not that you are given a random input omega, you generate something. And all these things, even though I wrote it in Stotanovich form, but we did it in Ito form with a correction. Somehow everything, so the things relies on the probabilistic things. So we actually want to understand a better understanding of the local theory. That's something via rough path or regulatory structure something. We actually want to have a more pathwise understanding of how the solution looks like locally. And that would be particularly useful if we want to do a more singular noise, which we don't know how to treat at all. And the third thing is that we try to move into more physical situations, is that we treat more singular. We want to treat more singular and also more physical noise. The most interesting thing probably is the white noise in space, but doesn't depend on time at all. And then there are papers by Arnaud Dabuche and Hendrik and also Massimiliano in the white noise in space case, but with sort of a nicer initial data somehow. And we are not able to treat it here. But what I feel is that if we want to treat it more singular cases, we have to have a better understanding of the structure of the local solution, rather than just the current statement. So, yeah, I think I'm a bit faster than I expected, but I think it's a good time to stop. Thank you very much.
I had a question where you discussed like the future, no? And you said in focusing you want to understand the blow up. Because why you're assuming there is blow up?
Well,
it could be that the noise prevents the blow up, no? Because it's perturbing the solution.
That's a good point, yeah.
Yeah, so you don't, so, I mean, this is a claim that you think there is blow up, or you?
I think there is blow up, at least in the supercritical case.
Okay.
In the focusing supercritical case, there is blow up, but in the focusing critical case, you are right, I don't know.
I mean, the blow up is just because energy concentrate, but the noise maybe just...
Maybe Maybe.
It's a bit of I don't know.
Oh, that's a good
I don't
point.
have any intuition, so I just wanted to know if you did some simulation or you
I don't. Yeah, then in terms of Max's comments, then actually it's better to remove these things. So if there is non-blow up, we change this into global. And if there is blow up, what are the mechanisms? You are right. It is possible. Yeah, in the deterministic, there is definitely blow up. But you are right. It is possible that things can magically get
It would
better.
be even more interesting because here you are just treating the noise as a difficulty, but actually the noise could help you to get different behavior from the PD.
So basically, it would be interesting to construct some bad initial data which blows up for deterministic case, but you sort of construct a noise in such a way that these things go right. That would be very interesting, I think. Yeah, thanks.
So in the same spirit, for the scattering, are there any expectations that you will be non-trivially perturbing the scattering for the deterministic case?
What do you mean by non-trivially perturbing?
Or your scattering relations or scattering results are qualitatively different?
Oh, I actually don't know. So even if we mimic the deterministic case, we don't know how to do it with the critical nonlinearity. We sort of did it without the nonlinearity at all. So with the linear equation, we did for the scattering, but with the nonlinearity, we don't do it at all. And there's one way you can do, in the sense that also did in Zhang's paper, is that you divide by something very large. I think what he divided, well, because this is Weijun time, which is a Brownian motion in time, I think what in Zhang's paper, he divided by t to the half plus kappa. So essentially the noise has finite quadratic variation. So essentially there's no noise after a long time. So if you divide it by such a large thing, you can have scattering, but what we are thinking of is even if you divide by something, it should be t to the some small power, but not so large. But even in that case, we still haven't figured out how to do it, but without the nonlinearity, we sort of did it in a simple way, but with the critical nonlinearity, we still haven't figured out, even if we mimic the deterministic case. The main thing is that you don't get street chart estimates. So the main thing is actually you want to get a street chart estimates for an operator like IDT Laplacian plus Laplacian psi equals psi like W dot. So you basically want the street chart estimates for this psi, and so usually, so in deterministic case where there's no Brownian motion, so the street chart estimates actually follows from dispersive things. So dispersive or the decay actually implies street charts, but here, if we have a Brownian motion, so the time cannot be reversed somehow. It's not clear how to get street chart estimates in this case, and street charts are actually essential to establishing scattering in the nonlinear case. But we are sort of thinking if it's possible to thanks.
Are there any further questions? If not, before thanking the speaker again, I'll just remind you we're going to take the group picture outside in a couple of minutes, and so thank you again.